DeepLearn for inviting me to give these series of talks. My name is Rex. I'm an assistant professor from Yale University. I've been there for, I guess, 3 to 4 years now. I primarily work on geometric deep learning, foundation models, multimodal models, some of which have been covered by many other lecturers also. Prior to that, I graduated from Stanford University, computer science department, focusing on graph representation learning. And yeah, so that's my kind of brief introduction. Happy to be here. And I believe that this series of lecture is a little bit more mathy compared to some other ones that you've seen over the past few days. But I try not to overwhelm you with a lot of formula. In fact, even if it's kind of mathy, there is very little formula that I will talk about in detail in this lecture. I hope that the high-level intuition kind of makes sense. And even if you kind of miss some of the details, I think it's perfectly fine. We already have a lot of libraries, so even if going back, like after you actually want to try things out, there shouldn't be any barrier to doing that. And I'll explain why that is the case. And can I just before the start of the lecture, can I have a quick show of hands, like how many of you are kind of or how many of you are familiar or some know a little bit about differential geometry? It's kind of a rare skill. Okay, great. That's okay. I will go through the basics. I don't think it's that hard to understand. As I said, there's not much formula, so don't get nervous. All right, so we'll get started, and the kind of a topic of the lecture is to connect graphs and geometric deep learning with foundation models. And I will talk about LLMs, and I will talk about why that is relevant. I will talk about why geometry plays a role in developing these foundation models. I think this is a super new area that we just started to appreciate. I've been working on this topic for the past maybe around 2 years, and it has now, like, we're now getting a lot of interesting results and great things. And I think this is something that in future there could be a lot of potential. So I just hope that you guys are very interested. All right. So yeah, so this is, I just posted some introduction of myself and my websites and core contributors that are kind of related to the content of the talk. All right, so the tutorial, or I guess the 3 sessions, are going to be organized as follows. So I will see at the end if we have extra time, and if we have extra time, we can talk a little bit more about foundation models and structured data, I guess graph representation learning in general. But for now, the first topic is going to be some preliminary, so I will talk about why we even study this and why that is kind of relevant for things that are, for general foundation models, including natural language, images, and etc. We'll talk about basic building blocks. How do we build neural networks, or in general foundation models in alternative geometry, and why that is important. And finally, I will talk about various foundation model development, what we have done, the roadmap, libraries, tools, and everything that kind of get practical and detailed. We'll cover things like hyperbolic language models, transformers, hyperbolic vision foundation models, math, or I guess fine-tuning, many different things in alternative geometry. And we want to show that this entire toolkit is there, and there is a lot of potential in doing those things. Okay. All right, so I guess we'll start with the part 1, which is the preliminary, and that's, hopefully it takes around maybe 2/3 of this session, and to get people kind of an intuitive understanding of why that is important. Okay. And part 2 is going to be this afternoon. We'll talk about building blocks, from things that are very basic, right? Even we start with things like residual connection, which is basically addition, right? Linear transformations, normalization, various things that are super basic to building MLPs, ResNets, CNNs, GNNs, transformers in general. And then lastly, we'll talk about more complex components that are used in building pre-trained large-scale foundation models such as large language models. All right. So we'll get started with background, the first part is basically motivation, like why we care about it. So instead of directly jumping into geometry, I wanted to start with a very simple example in natural language, right? So in foundation models, we typically deal with large amount of unsupervised data in different kinds of modalities. Right? Firstly, we have natural language, and we have tabular data, we have graphs, we have time series, we have images, we have videos, 3D objects, et cetera, et cetera. Okay, but I'm just using one example here, but you will see later why this is kind of prevalent in all kinds of modalities, and this will get philosophical, but I'll talk about those later. Right, so let's get into something kind of more or less concrete. Language models are built on token relationships, right? So it's not just the embeddings of tokens, it's that these tokens are contextualized, which means that these tokens are being put into some sentences or paragraphs, and the embeddings kind of depends not only on the token itself, but also on the context, right? When modeling these contexts through things like self-attention, which I assume everyone knows, what is being modeled, right? Intuitively, it's about word transitions, right? How different words leads to another different word in this kind of basic form of autoregressive next token prediction, right? And things like co-occurrence, typically after a certain appearance of certain words, the next word is likely going to follow certain distribution, and you can make predictions, right? So certain words co-occur with each other, certain tokens never appear together, right? And finally, if you want to get a little bit more kind of into theory, there's also mutual information, right? Different words carry different kinds of information. Sometimes they're similar in meaning, some different in meaning, and those things are being captured when they appear in the same context, right? So all these things are about relationship between tokens, and that's also the starting point here, right? So when you talk about relationships, one simple way of investigating it is through this co-occurrence matrix, right? So I'm assuming that you have, I'm giving an example of a very small corpus, right? So these co-occurrence numbers are not very big, but imagine that you have like 1 trillion tokens, right? So you can build like huge tables where you can kind of plot out how words can co-occur together. So this is a very primitive form of language model, which we don't use now, but it's a good tool for us to analyze and intuitively understand, what this could look like, right? What the underlying distribution of words and context could look like. It's some things that are immediately obvious, right? There are words that are very common. There are words that appear in all kinds of contexts. Right? Here is an example word, right? And as a result, the number of tokens or the number of co-occurrences with all the words are kind of high, right? It's very frequent. Not all the tokens are equal, right? So this token, for example, is very common, but it's not the case for some other tokens. So here are some other tokens that are very specific, right? They don't appear in all kinds of contexts. They have a very specific meaning. They're very concrete, right? Like flows, for example. They only appear in certain contexts, right? You don't have that word in all kinds of different scenarios, right? So they're very specific. But then we notice that there are a lot of these words, right? So this sort of follows this kind of scale-free or power law distribution of things, right? Which in general is kind of true for many different modalities and many different use cases, right? You always have a few of these things that are super important, commonly used, appearing in all kinds of contexts, and then you have a lot of words that are kind of specific, very rare, like appearing in a very specific context. So it's kind of a long tail distribution, if you will, right? And this generally is true for a lot of these unsupervised tasks, right? So why is that important, right? To kind of visualize it better, we can come up with this notion of co-occurrences, right? So we can basically formulate it as or visualize it as a graph structure where every token is represented as a node, and if something co-occur very frequently together, you sort of connect them with an edge, right? And imagine what that would look like, right? So it would most likely going to be like this, right? Of course, you know, in real world, right? You know, our vocabulary is, say, hundreds of thousands of tokens, right? And the entire corpus is like trillions of tokens. It's super big, right? I have no way to show it on the slides, but you get the idea, right? It's going to be like some kind of words that co-occur super often with almost everyone. And then when you kind of get down through the hierarchy, there are words that appear less and less often, right? But there are more and more such words, and you know, those words co-occur in a very specific context. We don't see that a kind of connection to every other word, right? It's only going to co-occur with certain words, most likely. Okay? So far, I think so good, right? It should be understood. Okay. So this is what we do. Like, there is certain kind of hierarchical structure, or you know, this kind of scale-free, long-tail distribution of tokens in natural language, and this is actually true for images and for many other things as well. But I'll talk about those later. Okay. That was just an anecdote, right? So this is just an example of how these token distribution could look like. You know, we are actually dealing with a huge corpus, like the trillions of tokens. So does this kind of intuition, like this hierarchical scale-free pattern, also hold true in other, so like in general, right, with the trillions of tokens? So we make sure, you know, you of course you cannot visualize that thing, right? That graph is going to be huge. You can't even count, right? It's too big, right, to compute. So as a result, usually we can resort to statistics or plots to understand what this distribution will look like, right? What if you were actually going to plot that graph, what that structure is going to look like, okay? So here is an example of how we do things. So let's focus on the two plots on the left, right? The first one is text. So we're using Llama 3.1 billion as an example LLM to embed all the tokens. And the second one is the image foundation model called Llama Gen. So we are basically encoding image patches into embeddings and do this plot. But you know, ignore the second one. Like, let's just focus on it. It's the same thing, right? Kind of telling the same idea. Okay. So we are embedding all these tokens in different kinds of contexts. And then we look at two things. So on the x-axis, we plot words with different frequencies. So words that appear very often will appear on the right as a dot, right? Words that appear less often will appear on the left. Okay. On the y-axis, it's going to be count. So how many of these words are there? All right. So this is a very typical scale-free or power law kind of plot. As you can see, you know, all the axes are on the log scale, right? Very obvious thing, if you look at the bottom right of that plot, there exist maybe a few words, right? Less than 10 of these words that appear so often, right? Appear 10 to the power of 7 times or like something, right? In this particular corpus. But then there are very few of these words, right? Less than 10 of them. Okay. On the other hand, you can see a bunch, the part on the top left, right? So these are tokens that appear very little, right? Their token frequency is like 10 to the power of 1. Okay. So like they are very rare words, but then these kind of words happen a lot, right? So you know, their count is like 10 to the power of 4. Okay. So this is an example corpus, but this is also generally true in many different corpus as well, which I will show later as well. So just for record, this is run on a sample of a red pajama, which is kind of a subset of a bunch of these sources from Wikipedia, Stack Exchange, GitHub, you know, all these text corpus, and we also run it on other data sets like mathematical reasoning and things like that. Right, so this distribution generally holds across different kinds of corpus. Okay, so that's the first thing, which kind of confirms this power law or this scale-free distribution of these tokens, right, appearing in real-world context. Okay, so the second part of the plot is more on the embedding space. We are investigating token norms, right? In this case, so every token appearing in all kinds of different contexts will get a different embedding, right? Embedded by, let's say, llama 3.1, and we can compute the average norm, like for each token, you can compute the norm of it, which is the length, basically the length of the vector, right? And then you kind of average that, and you treat that as the token norm, and we kind of look at the distribution of token norms across all the tokens in the vocabulary. Okay. This is just I think there's a very intuitive explanation, and you can visualize why that is the case. But imagine that you have a lot of tokens that appear very less often, right? So they don't appear often, and then you have a few tokens that appear very, very often. How would you kind of organize the embedding space if you were the deep learning model, right? A very obvious way is that I kind of organize the space according to the norm of the embedding, right? So if the norm is very small, you have a small circle, right? You have a small space, and you can put a limited amount of words there. And then if the norm gets bigger and bigger, you have bigger and bigger space, and you can put all kinds of words there. Okay? So if you were a deep learning model, I guess that's one question. There are these words that appear very often, but there are very few of them. Would you put them in places where it's kind of within a very small circle, or like kind of within a very big circle? Just a quick intuition kind of question. Yes? Why is that? So you're talking about words that appear less often. So I'm talking about these words that are more often, but there are very few of these words. Yes, exactly. Yes, exactly. So that's a very good intuition. That's correct, right? Imagine that you have very few words that are very often. Things like the, right? Things. The things that appear in all kinds of different contexts. You will put them in the center, right? You will put them in the center because they kind of connect to everyone else, right? But and then because there are very few of them, you can afford to put them in the small space, right? In comparison, if you have like exponentially big number of words that appear less often, you basically put them everywhere, right? You can afford to have a bigger norm because it's like a bigger space, and just put them everywhere. They don't need to be connected to any other tokens, right? They just need to be connected to a few tokens that are very relevant. Right? You just put them everywhere. Okay. So yes, that's exactly the intuition, and this is what we kind of see. If you look at the plot, the embeddings. There are a few of these tokens, very few of these tokens that are closer to the origin, right? So like embedded within a very small circle, right? And then there are a lot of tokens that have bigger norms, so they can be embedded everywhere else. Okay, that's even true in the Euclidean geometry, right? And the other thing is similar, but you notice that this is not exactly kind of a power law that you would imagine. It's not like as the norm increases, you get like more and more. But at least the first part of it is true, right? So I'll talk about why that is the case. But that intuition is correct. Okay. So in order to analyze what the underlying structure of the token is, firstly we resort to statistics or plots, as we mentioned, and the second kind of thing, a tool that we use is a metric called hyperbolicity. So this is a metric that intuitively measures how close your underlying structure is to some kind of tree structure or hierarchical structure. So here's an example. If it's a perfect tree, so this metric can be done on the graph itself. Basically, it's based by computing a bunch of shortest paths and doing some addition, subtraction there, and you will get this metric. But it can also be brought to the embedding space as well. So all you need to do is by replacing the shortest path in the formula with Euclidean distance of the embeddings, and that will be it. Right. But yeah, so these are measurements on the structure itself. So if you have this thing being 0, it's like a perfect tree, right? So perfectly hierarchical. And the larger the value is, so this is normalized, so I go from 0 to 1, but yeah. As it gets larger and larger, the less tree-like it's going to be, right? So as it gets larger, there is going to be a lot of small cycles, and that's going to, kind of violate the tree kind of structure, right? So larger and larger means less and less like a hierarchy, or less and less like a tree. Okay? And we can compute it in the embedding space, right? So why do we compute in embedding space? Because we simply don't have the underlying graph structure of all the natural language token distribution, right? As I said, you have 100,000 tokens, a trillion appearances of all these different tokens. So computing that graph is just impossible. Instead, we can compute it in the embedding space, right? We can look at all the embeddings and we can apply this formula and check the hyperbolicity. Okay? So here are a bunch of real-world experiments we've done. Right? So we start with the models on the left. We tested with encoder-only models like Roberta, which is a variant of BERT. We tested with Llama 3.1, some form of GPT-2 that was open source, and Gemma as well. But later on, this is generally true for all kinds of large language models, even like the most up-to-date ones now. So in terms of corpus, we tested things like archive, C4, Common Crawl, which is like a general text repository, GitHub code, Stack Exchange, Wikipedia, different text corpus. And the hyperbolicity values are listed here, and they are more or less consistent. Right? So as you observe, these hyperbolicity values range from 0.05 to 0.15 or 0.2, so which means that it's on the hierarchy side of things, right? So these are look like trees. So these are references. If it was like a perfect tree, it's going to be 0. So these values are not 0, but then they're not very big, right? If let's say if it was a dense graph of say or like some citation graph, some other structure that we're seeing, they have like typically much larger hyperbolicity. So 0.1 is typically considered very tree-like or very hierarchical, although it's not a perfect tree structure. Okay. So one question is how do you bridge the gap, right? As I said, we cannot even guess the underlying graph because it's so huge, right? As a result, we compute it as a kind of like a proxy measure in the embedding space, right? How do you make sure that this value, when you compute it in the embedding space of these large language models, is going to be consistent with the underlying structure, right? If you were to compute the graph hyperbolicity, which is too expensive to compute. Right, so here is a kind of approach that kind of verifies this idea. Generally, you observe kind of positive correlation. So we did that in a synthetic experiment where we had like a small corpus and then we do this correlation. We realized that if your embedding hyperbolicity is small, usually your graph hyperbolicity is also small, and vice versa. So it's like generally positive correlation, which confirms that if these values are low in the embedding space, that means the underlying structure is most likely also going to be hyperbolic or most likely going to be kind of tree-like or hierarchical in that sense. So that sort of completes the reasoning of the motivation. Okay.